So thank you for the introduction. Today, I started another talk about ergodic Markov processes. So the title is Subexponential lower bounds for f-ergodic Markov processes. It ends So what I'm interested in the spirit of this conference, we are working with a Markov process, and we would like to characterize its invariant measure. For instance, it's M-tail, and characterize the tails, see how heavy they are, and also we'd like to understand its rate of convergence towards the invariant. Well, as you know, this question is very classical. It has been extensively studied in literature. However, most of the works in literature are focused on one-sided bounds. So there are a lot of upper bounds. We saw a talk about that today already. But in comparison, the literature on lower bounds is very scarce. And even in very fundamental examples, we don't know what the correct lower bounds are and whether the upper bounds, the asymptotic rate for the upper bounds is actually optimal. So let's put that into some context by looking at a simple example. So what we have here is an ergodic elliptic diffusion. And again, in the spirit of this conference, this choose parameters in such a way that its invariant measure is heavy tailed, heavy polynomially tailed. So how does this look? This is in Rn, where n is arbitrarily large dimension, and P is such a drift that it pushes the process to the origin, making it positive current, making it ergodic, and we permit state dependence. Actually, we don't just need some state dependence, but we let this variance grow to infinity. So we have unbounded instantaneous variance. Now, this is a classical model. It has been studied in terms of upper bounds via Lyapunov function approach. And the result from Ford and Roberts from 2005 shows you that the process is ergodic, has a polynomial stationary measure, there are polynomial upper bounds in the stationary measure pi, and on the total variation distance, there exists upper bound on the rate of convergence, polynomial upper bound, explicitly in terms of model parameters. And the natural question is this bound asymptotically optimal? To the best of our knowledge, we don't know. So the proofs and the methods that give us the upper bound give us no information about lower bound, and we don't really know what's the optimal rate of convergence. And the work today will be dedicated to finding functions that bound this quantum equivalent. So before we go directly to lower bounds, let's remind ourselves how these upper bounds are obtained. So the direct definition, the upper function approach to the upper bounds is very general, and it doesn't require a lot of stuff. So we start with an irreducible Markov process on a locally compact space X, and this is the setting of the theory. Now, working on with such a general process can be very difficult. So the trick of the Lyapunov function approach is the following. One can take a Lyapunov function, so transformation from the state space to the interval 1 infinity. And then, because these processes on locally compact spaces tend to be nice, all asymptotic quantities can be captured in excursions from compact sets. So instead of looking at a complicated process on some complicated space, you map this process on the interval 1 infinity to observe excursions from a compact set. And this will capture the bounds on the invariant measure, and via coupling, when you hit these compact sets, the upper bound to the rate of convergence. And all these quantities, all these bounds on the excursions are captured in the drift process. So all these bounds are explicit in the drift of the process, which we get by mapping the state space one and infinity and looking at this process v of x. So we have this very broad setting, very general setting, one transformation, and from this one transformation, we can read off upper bounds on the tail of the invariant measure and on the rate of convergence. Now, this result is, in this sense, the result is incredible because it's so general, but it has a certain significant drawback. And that's the fact that everything relies on this essentially arbitrary choice of the optimal function. So if the choice of the optimal function is bad, then those bounds can be arbitrarily bad. So purely on a from theoretical level, if you show that convergence rate is polynomial and phi has polynomial upper bounds, we don't really know if that indeed is the case. And there are very easy examples when you have exponential convergence and exponential upper bounds, but you can choose such an optimal function that you just get polynomial bounds. So you have exponential ergodicity, but bad optimal function just gives you polynomial bounds. And that naturally motivates, again, the study of upper bounds, which is what I will describe. So what kind of result, now we can ask ourselves what kind of result in the lower bounds we want to have, what kind of theory. And the idea is that we want to classify lower bounds the same way as upper bounds, classified under minimum assumption. So we just want to assume irreducible Markov process on the local complex space X. And because the upper bounds theory already gives us upper bounds, and the lower bounds theory will give us lower bounds, we are actually going to have optimality, even though the conditions are going to be very bad. So what's our theorem? Well, the whole theory, again, rests on the choice of the optimal function. So we work with the general ergodic Markov process, and we have a optimal function v from the state space to the interval 1 infinity. But this time, instead of looking at dynamics of the process v of x, we look at the process 1 over v of x. And instead of bounding for the upper bound drift conditions, you essentially bound the magnitude of the drift of the process v of x from above. Here, we bound it in the magnitude from below. And essentially what turns out to be the case is that for the upper bound and the lower bounds, one needs more information than for the upper bounds. So we must also know the probability that if the process is between points L and R, we know the exit probability. We know the probability of exit of R. And with these two, with this drift condition and this additional fact, can be in practice easily checked. We get lower bounds on the rate on the tail of the invariant measure, and lower bounds on the rate of convergence in terms of this function phi and psi. So this looks somehow anticlimactic, since this is a main theorem, but we have some strange drift condition and some function which somehow depends on it. So to really understand how it works in practice, I'll spend more time talking about very classical examples where upper bounds are standard, known for more than 10 years, and lower bounds are, to the best of our knowledge, not known. The first example is the motivating example, which you saw on the first slide. So again, we have elliptic diffusion, polynomial tails in the invariant measure, the drift that makes it all work, and unbounded instantaneous values. Eventually unbounded. So with parameter L is 0, we can recover we bounded instantaneous variance and no state dependence, but we cover these general cases with state dependence as well. And we can find our functions L, phi, and psi. And this is very easy to check because it really just amounts to simple distribution, which is because the function 1 over is actually going to be bounded. In our case, even easier to check than, in some sense, even easier to check than upper bound condition. And from these three functions, we can construct a lower bound on the tail of the invariant measure, where here we have the explicit formula for the function we saw on the previous slide. And moreover, we get bound on this general F convergence towards the invariant measure. So in particular, F convergence is a generalization of a total variation distance, which accounts for convergence of moments. And with the case k is equal to 0, this recovers a lower bound to the total variation distance. And now the main question, are those bounds any good? Well, it turns out that the bounds, our lower bounds, match the well-known upper bounds from the important results. And yes, this holds for general convergence moment, but also for the total variation distance. And now a few natural questions that appear here. The first one is with Lyapunov function approaches. Lyapunov function approaches are very general, but the problem with Lyapunov function approaches is that you have to find the Lyapunov function. And this is potentially very difficult. But we had this in mind. So if you look at our functions, our function v is actually recycled from the upper bound theory. So this model has been studied in terms of upper bounds, and the upper bounds were obtained with the Lyapunov function. And to get lower bounds, you can use the same Lyapunov function and then get the functions phi and psi just by calculating the tree. So we don't have to come up with a new Lyapunov function. We can just find a good function for upper bounds and then plug it in our machinery and test it and get the lower bounds. So it really naturally complements the known fact, the known theory on the upper bounds. Another thing is that while this result doesn't look so bad because our bounds match, it's not very intuitive, because when I think about polynomial tails and Markov processes that converge to polynomial tails, usually I don't think about instantaneous variance that grows to infinity with a norm. So here is an example that's easier to understand, and that is Langevin diffusion in Rn. So here we just have a classical Langevin diffusion. It's with density norm of x to the minus alpha, and this is just a special case of the previous example. And what's easy to see is that yes, our bounds match, and we show that the curse of dimensionality is indeed the problem for a Langevin diffusion, and that because lower bounds match the upper bounds, it cannot be improved. So you see the derivation of the upper bound, the derivation of the rate of convergence is not just the upper bound, but in fact is the property of convergence for Langevin diffusions. Okay, so far we established lower bounds under some general conditions. So we had some variance and some drift, and we had asymptotic assumptions, and we assumed nothing in complex set. But we have assumed that tails were in both cases polynomial, and we have assumed that we know the leading coefficient. And let's try to look at something slightly more general. That is, what if the coefficients oscillate between two numbers in the variance, in the drift, and the variance. And also, can we treat another heavy tail distribution, so stretched exponential invariant measures, or as they're also known in the literature as Warwick distributions. And in this case, again, we can just apply the same function that was applied when upper bounds were studied, calculate the drift of the process 1 over v, which is just easily done using Ito's formula, and find a super submarket approximation, which gives us this probability that we exit on top. And this gives us, again, matching lower bounds on asymptotically matching lower bounds to the upper bounds on the tail, and asymptotically matching lower bounds to the upper bounds on the rate of convergence. Okay, so for the next example, and okay, also, while this wasn't written here explicitly, but actually, if we change parameters a bit, in this special case, we get exponential convergence and exponential tails on the invariant measure, and also our methods yield matching bounds in this case. So this work is primarily focused on subexponential ergodicity and heavy tails, but also for some exponential cases, we get matching bounds and can characterize, for example, which exponential moments are finite and which are not. So those were continuous time examples, and now we'd like to say something about processes with jumps. And we wanted a model where jumps wouldn't just be artificially added, but a model where heavy tail jump distribution severely affects the long-term behavior. And this is a Levy-driven FDE with some bounded but non-constant variance. And what's important, you see here, this is an OU type drift. So if you add Brownian noise, you get an invariant measure that's similar to normal, and the rate of convergence is exponential. And then we went back to the paper of Fortin Roberts, and we saw that if you replace Brownian motion with an extremely heavy-tailed Levy process that has logarithmically decaying tails, the process runs with the, so if you replace this Levy driver with some Brownian driver with Levy driver that has logarithmically decaying tails, then the process X remains ergodic, but it is no longer exponentially ergodic, but you get polynomial ergodicity. And again, we wanted to see if polynomial ergodicity is optimal, and we applied our methods. We used, again, the same Lyapunov function as for upper bounds, and we got matching lower bounds on the tail of the invariant measures. Now, this model is interesting for various reasons. One of them is that while these Levy processes can be utilized for a very large family of Levy processes. So we can have a +1 point process, we can have a process with very high path variation, and we can also have different types of sort of symmetry in jumps. So you can have only positive jumps, you can have jumps that are extremely heavy to both sides, and this will lead to very different, very non-symmetric invariant distributions. So in the case when jumps are only positive, you will have the whole process sit in the positive real line, and when the jumps are, when we have very heavy negative jumps, this leads to invariant measure, which is heavy tailed in both negative and positive direction. And in this example, we wanted to show that our method is robust and doesn't require symmetry in the behavior of the process. Another interesting thing is something that people in the more applied probability have known for a long time, and that is if you look at decay in quantum, in the time, and decay in the rate of convergence is polynomial, so considerably faster. And in Langevin, what we had is polynomial decay, and in pi, and polynomial decay with a smaller power for the rate of convergence. So when faced with these extremely heavy tail distributions, just polynomial heavy tail distributions, it is very advantageous to work with something that jumps around very quickly and has a quick excursion, something like a heavy-tailed Levy process, as opposed to just Langevin Brownian dynamics.
Can I ask you here? Is it okay?
Yeah.
Can you have such phenomena in discrete time setting? Yes, very fast convergence with respect, yes, in comparison to stationary tail.
Yeah, so we believe so. We didn't. The paper is continuous time, so we didn't do it. But,
but you said it's some. You said you gave explanation which was essentially used based on the continuous time stuff. Yeah.
Yeah, so this is in continuous time, but we strongly believe that this can be generalized to discrete time. Okay, now those were the models we studied. There are just some remarks I'd like to make. So our results complement and extend the existing theory on Lyapunov drift conditions by allowing us to get matching lower bounds to the known upper bounds, and therefore use this Lyapunov function to characterize asymptotic behavior of processes. So far, at least from theoretical standpoint, Lyapunov functions could not be properly used to characterize asymptotic behavior, especially in the heavy-tailed cases, because you can always argue that the reason why you get polynomial upper bounds is that your Lyapunov functions not optimal. But now, with our approach to lower bounds, we can fully characterize the tails and the rate of convergence. Now, the second remark I'd like to make, and this will be relevant when I tell you something about the proofs and how the functions work, is that really this idea which we use to study convergence, to get lower bounds in convergence, comes from papers of Martin Heider, who studied some models in mathematics, some hypoelliptic models in mathematical physics. And he had this incredible insight into Markov processes with heavy tail distributions. And that is that if you have a heavy tail distribution in the process that converges there, then the bottleneck is going to be in the tails. The convergence will be slow because the process will not reach a heavy tail spot. But to fully go from these ideas to lower bounds and rates of convergence, one needs strong, explicit bounds on the tails of the entire plan. And these were in general not available, but with our new drift condition, with these functions 1 over v, we make these estimates available, and we can use these ideas to full force and get lower bounds for general bound. And now, another more theoretical comment is that f-ergodic Markov processes are connected to the question of behavior correlations and mixing times in ergodic theory. And not unlike the theory of Markov processes, mixing times and upper bounds and mixing times and decay correlations in ergodic theory came before lower bounds. And lower bounds were established in the seminal work of Sarig in 2002 by using some elementary ideas from probability theory. So in particular, it was the generalization of Rogojin's renewal error estimate. And the way to think about it is that if you have just a random loop on the lattice, then the rate of convergence, not in the invariant measure on the whole space, but just to the point, is connected to the renewal theorem because excursions from a point to random walk form are IID random variables. Then you can look at the convergence through this renewal theorem. The natural question is, if these ideas, elementary ideas of probability theory, were extended to lower bounds in general ergodic theory, why wouldn't we extend them to continuous time Markov processes? And it turns out that these ideas in ergodic theory would give a far less robust theory towards lower bounds as higher ideas allow. Because, for instance, we had a model where we don't know exactly what the parameters are. We know that they might oscillate between 2 points, but we don't know exactly what the parameter is. And in these cases, these renewal theorem approaches do not work because certain error terms don't. So this is some ideas on how we got there and some connections with the wider literature. Now, as you can see, the main theorem, I didn't explicitly say anything about how these functions that form the lower bounds look like, what they are, and why this strange transformation actually gives far lower bounds for a wide range of models. So I'd like to conclude by saying something about that. Now, before that, do we have any questions? Okay.
So I sort of know that, I mean, are you going to just describe how you compute these phi and psi?
Just give some ideas
on
how one goes from A to B to 1 and 2.
Okay, good. Yeah, then continue, please.
So one thing you can notice with this theorem is that it has very little structure. So if you have an ergodic Markov process, some usual condition, and some strange function, and then you get bounds. And because we have very little structure, we have very little tools to work with. And what we do is then go back to very fundamental and elementary ideas of Dublin, who understood that stability can be studied using excursions from Petit set. And again, we go back to the random walk lattice. And if you recall, if you want to measure how much does an invariant measure charge a single point, then compute 1 over the expectation of the excursion of the return point. And all other properties of the invariant measure are really captured in these excursions from points for the random walk. And similarly, to extend these ideas to continuous time, one looks at excursions from Petit sets. So what are going to be excursions from Petit sets? We are going to have a bounded measure set, some positive time because we're in continuous time. We're going to look how long does it take for the process to return to this set D. And what's going to be of special importance is not only how long do you have to wait to return to the set, but we have to understand the additive functional that captures the path of the process. And it's important that we understand this for a large family of functions. Now, the proof, now this idea, this is the quantity that will tell us everything we need to know. And the proof then reduces to 3 steps. The first one is we go from our lower bound drift conditions to lower bounds on this probability that the excursions, lower bounds on the tails of these excursions, and the fact that every Petit set is bound. And this is related to this is sort of converse to the upper bounds. The upper bounds, you usually prove that all compact sets are Petit. And here we prove that all Petit sets are bound. And then in step 2, one uses these Dublin's ideas that everything about invariant measure is captured in excursions from Petit set to go from these estimates of the excursion to the lower bound of the invariant measure. And in the last step, we use higher ideas that the lower bound on the total variation is captured in the tails to get the lower bound to get total variation, and in general, F variation. In some sense, step 2 is believable if you believe that everything for continuous time process is the same as for discrete time processes. And step 3, you'll see, is very direct. So really the problem is step 1. So how do you go from this strange transformation 1 over V to general bound on these excursions? So again, this is the condition. This is the strict condition. And I'll try to briefly explain how this works. So we start. So the only here in general, we want to understand how excursions from compact sets are bounded from below, but it's enough to understand additive functions of return terms. So we start above level L. And what we know from this point B is that with a certain probability, we're going to hit a very high level R. RQ and RQ, which is something like 4 times R, and we hit arbitrary level R. You know that before returning to L, we're going to hit that level. And what's the most interesting and creative part of this work is something I can't explain very well right now. But this transformation 1 over V in the drift actually tells you, after hitting this level 4 times R, let's say, how long the process will stay above level R. And because we already assumed that we hit this level before returning back to L, this gives us lower bound on this return, on this additive functional until the return time. And essentially, what's so important is that by, in some sense, optimizing over R and these 2 probabilities, we get lower bounds on these excursions that are sharp for a very large family of models, and this gives us sharp bounds on the tails of the invariant measure on the rate. And then you go from these bounds on the return times and additive functionals to the tail of the invariant measure. One just uses some seminal results of mine and Tweedy, which extends to continuous time. This fact that's well known, that was before well known in discrete time, and that is if this excursion, this additive function of the excursion is infinite, then this function is not integrable with respect to the invariant measure. If you plug in 1, you see that if the process H is 1 everywhere, you see that if the process is not positively current, then the invariant measure is not final. So that might be good for intuition. And then using what we have just shown, and the fact that because our approach is pathwise, this holds for all increasing functions H, we get the lower bound in the tail of the invariant measure. And then in the last step, this higher idea. So essentially, if you want to bound the rate of convergence in the total variation distance, the right way to look at it is try to look at the difference between how much does the invariant measure charge in the tail and how much does the margin charge the tail. And we bound the invariant measure from below and how much the marginal charges from above. And for most heavy tail distributions, the process will struggle to reach the tails, and this is why this is hard for a lot of models. And this was this incredible insight that Martin Heyer had, and we linked it up to have variation dependent convergence of moments as well. And in these cases, it also works quite well. So we get short bounds. And here, a small thing is that we've essentially introduced another hyperparameter, but this is with increasing function. But Yes, so I think that's it from me for today. These are the sources. And thank you very much.
So
Yes, me.
no, sorry. So regarding the function psi, you sort of alluded to the fact that you have like some kind of recipe to build these functions phi and psi. So phi came from applying like Ito's formula, right?
Yeah, so
Controlling something. But what about psi? Because you need a lower bound on some.
yeah, for quantitative convenience time, this is just the same as finding a function psi such that psi of B is a submark. It's just a submark via transformation. But if you work for dynamic processes, you can use some part see that the probability of hitting a high level increases are.
But you need a lower bound, right?
Yes, you need to go.
You just optional sampling theorem if you have bound jumps. So if you're continuous, then it's fine. No, that's a submarting illumination gives. Then you can get this kind of psi. Otherwise, you need to construct it if you have unbounded jumps. You can't use it.
There's no recipe, easy recipe.
Yes. Yeah. There's no such direct drift condition.
So convergence rates depends on initial condition, correct? On
Yeah.
X, on X.
Yes.
And so there is no yes. So yes, it may be very bad if you start very far away. Yeah.
Well, it
Yeah,
depends.
Yeah. Even if you may have convergence rates, exponential convergence rates starting from good points, like from a side set, and you may have much lower rate from another. So you have the same Markov chain,
Yes.
but you are doing for any initial condition. Yes. So so in this case, if you have very good convergence rates, you are talking about return times to the petit set, yeah.
Yes.
But you may start from a very far away, and then convergence rates are very bad.
Yes.
Yes, and it depends only on the initial value essentially, not on anything else. Yeah.
Well,
Hitting time from initial value, yes. So and it should be present somewhere there. And in this case, I think the situation is more or less clear. Yeah.
no, so the initial point. So when we use this analysis of return times to petit sets, we use it to characterize the invariant measure. So initial condition is not captured.
Initial condition. Yeah.
No, this doesn't have anything to do with it.
Yeah. So you put conditions on initial condition. Initial condition. Yeah. It should be somewhere there.
So here there is dependence on the initial condition.
Yeah, I understand. Another question is you're characterizing convergence rates. So yes. What you are doing something related to tails distributions. Yeah, but in some other situations there are some natural test function, Lyapunov function is just hitting time of a small set, mean hitting time of a small set. Maybe you consider this usually for any point x. Say Lyapunov function is a mean hitting time of this particular small set.
Optimal, yes.
Optimal. This is optimal. You can get better.
Yes.
It's used in instability results as stability. So essentially, yeah. So
Functions that appear here are somehow asymptotic to this kind of.
I'm saying, yeah. Okay.
Yeah, so what big difference between discrete time, continuous time, discrete time, continuous time versus you get very large, very. So I remember in when I was working with just on that paper, what making things very difficult was this possibility of basically going very high very quickly and then coming back. And we had to sort of account for that and what was happening. So in your description of the proof, I mean, you're talking about going from this kind of path bound B to the path bound but how do you get around this fact that actually you could go really high very quickly and then come down.
And we found the probability which we go very far very quickly.
Yeah.
But then this magic actually tells us with sufficiently high probability we will not return back.
I see, yeah. Because that, in some sense, that, I mean, tell me if I'm wrong. It basically, it's doing the opposite. It basically, it's the ordinary drift condition is pulling you back towards the origin.
Exactly.
This is pulling you towards infinity,
Yes,
right?
this creates a sub-martingale. We estimate how strong it is. This tells us.
Okay, so on that, I mean, so, you know, we often have to introduce, and it's a bit artificial, because I mean, the way you presented it, I really like that. Often introduce this idea of that V has to be like a norm-like function that goes to infinity and then tails and basically it's a bound. Have you got that assumption in somewhere? So basically you want V to go to 0 in the text, really, don't you?
No, V goes to infinity, 1 over V goes to 0.
Yeah, sorry, 1 over V is what I meant.
Yes, yeah, so this is hidden here, but what's important is that it doesn't have to go to infinity everywhere. So let's say you have a d-dimensional distribution that lie in d-1 direction, so make that heavy in 1 direction. You can think V that goes into jump in this heavy direction, so isolate heavy tail, which then gets our bound because the bottleneck is usually heavy tail.
Sorry, a basic question. I didn't really understand. How is the initial condition embedded in that too?
So this is in the, so we have bound on the invariant measure and then we compare how fast we reach the tails. And in this comparison, significantly depends on, because the probability that you the tail effect.
But there's no initial condition in that formula. Is that?
In this one, it is.
Sorry, little x is this. Yeah. As I say, a basic question. Yeah. All right. Great. Thank you.
In your examples, can you say anything about the constants? Because you had a little c on the left-hand side and the capital C on the right-hand side. So how do they compare?
If you look at these models under very general assumptions, we don't assume anything on complex sets because we want for general approach to these small ones. So this is too general to talk about constants. But except for this one results of mine and Tweedy, every bound we use here is non-asymptotic. So it's potential to know the bounds doesn't seem impossible. Okay? But for these general models.
Great. Thanks very much. Gareth, are you ready?